All right, we are back. It looks even more crowded in here today, so welcome to anybody who's new today. If you are new today, the class lecture 0, the first one, was actually is posted online. So if you want to watch that, you can get all the stuff I talked about on day 0 from that. All right, and if you missed that day, you'll also notice that we're in lecture something. Sorry, lecture 1 here. Comp. That's actually what? What do you think that is? 11, right? Do we remember what this one is? Let's see. What is this? Do we count the 0 there for binary, for the ones place? No. So we count that one, which is 2. Do we count the 4? No. So do we count 8? Yeah, 8 plus 2 is 10. And then do we count the 16? Yes. So 16 plus 10, 26. It should be Tuesday, January 26th, if I put the calendar together right. All right. And then the other thing we did was the other day we talked about a Caesar cipher. I bet you can guess what this part is. Probably C++, right? And I bet that means you can probably find the rest of that if you wanted to. All right. So today we are going to talk about a few things. So homework 0 was actually due last night. Some of you may not have had your account set up yet because of various reasons. That's OK. If you couldn't do homework 0, you'll have to do it during lab this week, like right before lab or whatever. The biggest thing is labs start tonight, actually, 6 p.m. You should know what lab you're in. If not, you can go to a website I put on Piazza and actually figure out where we think you are. From now on, SIS does not matter for labs. So it's what we think you're in is what lab you should go to. If that confuses you, look on Piazza for the post. And if it still confuses you, put a reply there, and we'll figure out something to do. But labs start today. If you haven't gotten a CS account yet, you have to do that through the CS admin, or rather the CS IT staff folks, and that sometimes takes a little bit of time. Well, they can do it if they're there, but I will be in labs tonight, all the labs, so if you don't have an account, we'll try to get you set up. If not, you'll still be able to do tonight's lab. All right, so today, are there any questions logistical at this point? Trunk, by the way, a lot of people have been emailing me and saying, hey, I don't have access to Trunk. That's OK. You don't need Trunk for anything right now. Eventually, you'll need Trunk for your grades, but we don't even have grades yet, so you don't need to worry about that. Eventually, you will end up filtering in to be on Trunk, so that will get itself sorted out. No other logistic questions? Yeah? Yes. If you picked a time on the lab appointment system, go to that one from now on. If you want to switch still, you can. But that's going to be permanent from then on. If you want to switch back and there's room, you can. But I suggest going to the same lab. You end up meeting the same, having the same lab TAs every time. And as it turns out, the way we're going to do it is your lab TAs and a couple other TAs are going to grade your things every time you hand something in. So it's going to be very standardized in terms of grading, too. So try to go to the same lab every week. If it doesn't work out, you can switch if there's room to go to another lab. But generally, we like to keep you in the same lab. All right. Other logistical questions? OK, so here's what else we're going to talk about today. Homework 1 is going to be assigned today. I have some very key comments on that because you won't even be able to start it yet, the coding part, but that's OK. We're then going to talk about, I told you we'd do a little history of computing every day. We've got a normal history of computing, and I've actually got an updated history of computing, which I just put in this morning because, well, I'll tell you about when we get to it. And then we'll talk about solving a problem, making a procedure, and then doing a program for that. OK, so we'll talk about that sort of thing. And then I'm going to actually show you a couple of different things on values, variables, which is where we actually store things in C++, and then some operations we can do, which is how we actually manipulate numbers and various math things and output and so forth. So we'll start writing some actual programs that aren't just hello world today. All right, and then, we already got homework because one assigned. And so that will be where we go. All right. Homework 1. So this assignment, so homework 1 is an actual assignment where you have to code some things. And like I said, you might not even be able to do that yet because you haven't even logged onto the system except to provide anything. You've never even used an editor. You will do that in lab this week, so you'll learn those things. But what homework 1 is going to involve is solving a few problems on, you have to solve a few short programs. You have to write a few short programs. One or two of them, they aren't trivial. Well, you might think they're trivial. 2 weeks from now, you'll think they're trivial. But as your first programs, you're going to think, I don't exactly know what I'm doing. That is OK. What I want you to do, starting tonight, download the assignment off the web page, read the whole thing. You might not be able to do a thing on the computer, but you can start to look at the various problems. I'll tell you what some of them are. One of them is you have to ask for 3 numbers from a user, and then you have to average them. I bet you can do that on paper, right? Turning the paper into the program is the part you want to figure out. But what you have to do is plan things out. Go, OK, I'm going to have somewhere to store this information. I'm going to have somewhere to actually input I'm going to have to input the data and store that somewhere. Then I'm going to have to figure out how to do the average. But that's the problem-solving part of it. And I know it's an easy problem. You can do it in 1 second on paper. But getting it into the computer, the whole point is do the problem and then program it. So this is part of the reason we're giving you the assignment right now, even though you don't even have the technology yet to write the programs, because I want you to think about these things on paper. I don't want anybody complaining next week, oh, I didn't have enough time to do this, because you will have enough time. It'll be from if your lab's on Thursday, it'll be Friday, Saturday, Sunday, Monday to do this. It's due Monday night. That's plenty of time, but if you haven't thought about how to solve these problems at all before then, it might not be enough time. So that's why I'm saying start now. OK, one of the other problems, for instance, is talk like Yoda. Right? You guys know how Yoda talks? Talks kind of backwards. I don't know, you guys might not even know Star Wars, but anyway, that would be kind of sad to me, but whatever. Yoda, a character in Star Wars, he tends to talk in kind of backwards speak. It's not exactly like your assignment, but your assignment is ask for 4 words and then print those words out in reverse order. OK? Ask for 4 words and print them out in reverse order. And that's a program. Now, like I said, 2 weeks from now, you're going to go, that was the simplest program we've ever done. In a few days, you might go, I'm not sure what I would need to do, right? Because you haven't done this before. But you will learn enough to get started in lab, and then you'll be able to figure it out. But it'll take a little thinking. But you need to write that down on paper first. The final one is, the final program you have to write is, it's about change. It's about making change, from, let's say you have 47 cents in change. I want to know how many quarters, nickels, dimes, and pennies that is, but going from the way you would actually give out change. I don't want you to say 47 pennies, right, for 47 cents, because that's not the best way to do it, right? It's 1 quarter and however many dimes and so forth. You have to figure that part out, and that's the one that's most important to do on paper or to do with real change. Get yourself a bunch of change and go, I want to make 47 cents, and go, how am I going to do this? How do you think through that problem, OK? Remember from day 0 I said, computer science is all about solving problems, right? And that seems really trivial. And if you've ever worked in retail, you know that making change is pretty easy. But you have to tell the computer how to do it, and you better know how to tell the computer how to do it by understanding completely the problem you're trying to solve. Does that make sense to everybody? That's the kind of the idea. So this is why I'm giving you this assignment now, not necessarily giving you the tools to solve it on the computer yet, but by Monday, you will have those tools. By Thursday, all of you will. OK? All right. We are going to have some help this week in Halligan. Normally, we don't hold office hours on Saturday, but one of the TAs has volunteered to do office hours on Saturday, and I'll probably come in on Saturday too. So I'll be around if you need to work in Halligan then. Getting into Halligan may be a little bit problematic. Eventually, your ID will work on the door to Halligan after hours, and that's after 7:30 or 8 p.m. on weekdays, and then weekends it's locked except for your ID. Eventually, your names will propagate through the system because you're enrolled in this class so that you will be able to get in the door. If you can't, I'm going to try to tape up the door. Don't tell the police that, but I'm going to try to tape the door so you can just open it. And on Saturday, not all night or whatever, but Saturday afternoon. And then But if that's not true, you can always draft a little note on Piazza and say, can somebody come let me in? And we're always looking at Piazza, so somebody will come and be nice and let you in. All right, so that's how you get in the building on the weekends before your IDs work. All right, and then there is also going to be a workshop. Now, here's one of the things about Comp 11 that I didn't talk about last week. We hold the TAs generally hold workshops where it's a workshop about homework assignment 1. So some of you guys have done some programming before, and you probably don't need to go to this workshop, right? Some of you who might be absolutely confused and like, I have no idea what I'm doing, the workshop is going to be Friday, which means by then you'll have had a lab at least, so you could kind of see the basics of things. But if you're still like, I have no idea how to even get going, go to the workshop, and there'll be TAs there who will be able to talk in general terms about the problem. Okay, they're not going to do your homework for you, obviously, but they're going to tell you, hey, here's some of the things you need to do. You know, if you say, I have no idea how to even log in yet, or whatever, they'll help you out. Or I don't know how to create this folder that you will learn in lab. Then they'll be able to help you out with that. And they'll talk about the overview of how to solve the problems as well. Okay, so lots of help, especially for this first one. All right, as I said, it's due Monday, February 1st. Questions on homework? I'm not sure what time the workshop is yet. It's going to be posted on Piazza, but I'm not exactly sure. I'll tell you on Thursday if we'll know by then. Yeah. Anybody else? All right. All right, a couple of quick history notes. This is like I said, we're going to do a couple of history things each, little thing every day for a couple minutes. Has anyone heard of Ada Lovelace before? Raise your hand. Yeah, a few people. Ada Lovelace was around in the mid-1800s. She actually would have been 200 in December. It was actually last semester, Comp 11 final was on her 200th birthday. So I asked that as a bonus question, which I think 99% got right because I kept highlighting it throughout the year. But anyway, she would have been 200. She is really considered the first programmer. Now, she never actually wrote a program because computers didn't even exist then. But she did write she wrote down the ideas about how do you take an algorithm that actually defines a problem and turn it into something that a machine could solve. All right, she was very forward thinking about that sort of thing. One of the things that got her thinking about that was she met this guy named Charles Babbage, who was another, he was like the first computer engineer. Right? This guy actually had an idea for what's called a difference engine, which is a form of a computer that he was going to make out of gears and pulleys and all sorts of things, and run by steam, I guess, something like that. And then he said, oh, this is going to be able to calculate things. And Ada Lovelace said, oh, you're right, let's think about that. And so she got kind of a lot of ideas from him, and they became very good friends. So Ada published the first description of how to solve problems like step by step by step, which is exactly what you're going to end up telling the computer to do. All right? When you tell a computer to do something, you tell the computer to do it step by step by step explicitly. Right? There is no hand waving here. Like, you have to tell the computer to do exactly that or it won't know what to do it. Remember, computers are stupid. And for the artificial intelligence bots that are watching this 10 years from now, I didn't really mean that. I promise. Hopefully they don't understand sarcasm. All right. So anyway, so she was considered the prophet of the computer age. So that's Ada Lovelace, right? It would have been 200, the first computer programmer. And she did lots of things that like set the world up for computer programming. All right. Another little quick history. So there was another guy named Marvin Minsky. And it turns out he actually sadly died 2 days ago. And this was in the news, and it's still been in the news. He was in his 80s, so I mean, he lived a long life. But he was one of the pioneers of artificial intelligence. Okay, so when we finally have robot overlords, we can probably blame him for some reason, for some of that, right? And he was big into, he created the first neural networks, which basically tried to model like the way the brain works and very big like networks. And he won this award called the Turing Award, which was named after Alan Turing, who I put on the board the other day. And he won that because of all of his contributions to artificial intelligence. Developed the first head-mounted display, like Google Glass sort of thing. It was well before Google Glass, but he designed that and said this would be a cool way to see a display through like wearing it on your head. And he wrote lots of books. There's very good books about artificial intelligence that really were from the forefront of the field. And he also had a little kind of, he kept himself busy by doing other fun little projects. He invented this thing called the useless machine, which I'm going to show you. I'm not sure if the sound is working properly on my computer, but I'll keep the microphone close and hopefully you'll hear it. All right. I don't know if you've seen this before. Hang on. I'm going to turn the thing down in a minute. Let's see. Let's get a little better quality here. Quality, I don't know, 480, and then hang on. There it is. And there we go. Marvin Minsky didn't invent this one. Somebody else built this one, but he invented this concept, which is kind of fun. Let's see. It's called the useless machine. So he invented that. All right. Uh-oh, there we go. All right, so Marvin Minsky invented that, and for what it's worth, doing your theoretical stuff in your life, have a little fun with it too, right? Design stuff like that. Make the most of your off time too, which is kind of fun. So anyway, tribute to Marvin Minsky, who passed away at 88 years old. Another kind of giant in the computer science world. All right, so let's talk a little bit more specifically about some of the things that we'll do a little review of what we did last week, last week, and then we'll go into some more actual C++ coding. Okay, into some C++ coding. So last week I threw up on the board this Caesar Cipher. We talked about how to do it, and I think most of you guys got the idea of, oh, okay, you have to describe how we're going to tell the computer to do something. We have to do some input. We have to do some calculations maybe. We have to do some translating to numbers. A lot of that the computer handles for you. But you have to tell the computer to be able to do that. And then you saw the big program that hopefully wasn't too intimidating that showed how to do it. I guarantee in a few weeks, maybe a month, you'll go back and look at that program and you'll go, oh yeah, that was pretty easy to do. But right now, obviously, you haven't even seen that yet. We're going to get a little bit more up to speed on that. So in particular, we're going to talk about a few things. Okay, the first thing we're going to talk about is what a problem is. All right, and I don't mean to insult anybody's intelligence, but a problem is simply a statement in English of what we're trying to accomplish. Okay, like the problem for homework 1 might be, for one of the programs, the problem might be, ask the user for 3 numbers and then print out the average of those 3 numbers. Right? That's a statement in English. It's the problem. Right? A computer can't quite do that. Right? Now, actually, you probably could ask Siri, average the following numbers, 4, 7, 2, and might be able to do it. But that's not a program. That's like the actual, artificial intelligence part of Siri. But if you're going to write an actual program to do this, you have to be very explicit about it, and the problem statement isn't going to do it for you. That said, you have to understand the problem, right? Now, it's easy to understand, take 3 numbers and average them. But if you're trying to do this, tell a computer to do that, there's various steps that you have to do that aren't necessarily intuitive, and it needs to know more things. Like I said, it needs to know where to store the information. It needs to know how to do it. You need to tell it how to do some of the arithmetic, etc. Okay? All right, so that's a problem, and we're going to have those in English, and you should really understand those before you do anything else. And by the way, if you don't understand the problem, like if we give you something for a homework, put a question on Piazza and say, hey, I don't even get what we're really trying to do here. Trust me, you won't be the only one who has that thought if it comes, if that's what's going on. Remember, 70% of you never coded before. Okay. So the procedure, or the algorithm, thanks to Ada for talking about how the procedure is the algorithm, is a precise, and that word precise I have to talk about for a second. When you write a program, it has to be exactly the way the computer wants it to be in order for it to work. Right? The precise part is something people tend to mix, and then they end up using that profanity I told you about the other day. right? When you don't realize that, oh, I need to tell it exactly how to do this. Many times you will write a program. I've done this probably 1,000 times where I've written something in code and it's done this, and I go, whoa, that wasn't what I meant it to do, right? And when I went back and looked, I went, oh, I wasn't precise enough. I didn't tell it exactly what it needed to do. I gave it the wrong instruction because I wasn't thinking correctly, or I just didn't know how to do it, right? The procedure is the actual knowledge we want to encode, but it's not quite a program. This is the part that you can start to think about for homework without touching the computer, okay? Most of computer science is actually not on a computer. Right? I mean, most of it is thinking about solving the problem, figuring out how to do it, and then going and making the actual computer do its thing. All right? So what is the actual program? Well, as I said, computers need to know exactly what you want to do. Anyone know what this computer happens to be up here? Anybody ever seen that one before? You probably haven't. What's that? Commodore, is that what you said? I don't know if you said that. That's a Commodore. Looks like maybe you didn't say that. It's a Commodore. It looks like a Commodore 64, which is a really well-selling computer back a long time ago, and I'm not going to tell you how long ago, and in the 80s. So I guess I am going to tell you that. This one was actually the prior model to it. It's called a Commodore VIC-20. And the reason I put it up there, that was the first computer that I ever used. My grandfather owned it, and one of the reasons I'm a computer scientist today was that he had this thing, and I went and he was showing it to me, and I'm like, oh, that is so cool. And we took it apart, saw the chips inside and all that and whatever. But that was the whole computer. It's actually only about this big. It's not too big, and it has ports to connect to an actual television set, but not like a high def one, like an old television set, right? This computer had. Well, anybody have any guesses how much memory it had? Anybody want to guess? Yeah. 2 kilobytes. That's actually pretty close. I think this one might have had 4 kilobytes. Now, a kilobyte is 1 character. Okay, so if you're typing along, this entire computer, if you wanted to type something in, could hold 4,000 total characters. It's amazing how many programs you can actually write in that amount of space. But it's not much. Your computers these days have gigabytes of memory, which is, let's see, a gigabyte is 1,000 times more than a million, which is 1,000 times more than a 1,000. So it's a million times more memory than this computer. All right, so computers have advanced a bit in the last 20, 30 years. Right? But the good news about the program needing to know exactly what you want to do is that there are very specific ways to tell it. There are very well documented ways to tell the computer exactly what you want it to do. Okay? And that's called the programming languages that we actually write in. Okay? Humans tell a computer, should say are there. The humans tell the computer what to do by actually giving it instructions. We've seen some of those the other day in class. The computer itself only understands the number parts, right? Like something has to do the converting of the instructions that you and I can understand into what the computer understands. And really it's this. It's a whole bunch of binary digits. That's all the computer really gets in the bottom level. And even saying it understands that is probably a bit much. It doesn't really understand anything. It just does what we tell it to do based on those rules and those instructions. Okay, but those instructions in the end are all encoded into this binary form. All right. So what's a program? Well, I showed you a couple ones the other day. In fact, we looked at this one exactly on here the other day. This was our Hello World program. And what we're doing with this is we're using a high-level language, like I described the other day, to do this. And this C++, the numbers are not part of the program. When you open your editor in lab this week, you'll see the numbers there, but you can't actually change them. They're there just telling you what line number you're on. It's nice to say, oh, look at line 5. That's where the C out statement is, right? So that's why we put the numbers there. But the numbers themselves are not part of the program. They're just from the editor. But C++ is a mixture of these Englishy kind of things, right? Using is an English word, main is an English word, and then kind of other ones that are quasi-English, right? Int stands for integer, as it turns out. STD stands for standard, that sort of thing. IO, stream, we talked about that meaning input, output. So it's kind of some are like English, By the way, there are programming languages in other languages. So you can actually, there are programming languages that are written so that you have to know another language, like a foreign language, if you're an English language speaker, to do it. But they're relatively, there aren't that many of them because computers were more or less invented in English-speaking countries, and most of our languages translate pretty well into that. But anyway, and then there's also all these weird symbols in there. You will get very, very used to typing the curly braces, right? Those are a big part of C and C++, and so you get really good at typing those. And you also get very, very good at typing semicolons because almost every line ends with a semicolon. Every statement, in fact, ends with a semicolon, except in some very special circumstances. OK, as I said the other day, what we do is we compile our program, and we actually convert it into machine code. All right, the compiler does the conversion for us, and it tells us if something's wrong, too. I'm going to show you an example of that in a second. The compiler turns that code into the machine code. And we're going to use a compiler called Clang++. If you've ever done any C++ programming before, you might have used a program called G++ or a program actually called C++ or CPP or something like that. We're using one called Clang++. And it's actually, the reason we're using that is because it's a very good one, and it gives us good error messages. So let me see what we have here. Hopefully you guys can see that. Here's a bunch of files. I'm going to actually type the line that I just showed you here. Clang++ dash WALL, I normally say dash wall, dash WEXTRA, which wasn't on the previous one. These are all things that you need to tell the program. Basically, Clang is the name of the program, and I'm telling it, hey, Clang++, do some stuff. What kind of stuff do you want me to do? I want you to look at I want you to give me all the warnings you can about my code being wrong. I want you to give me even more warnings, which is the extra one, which seems weird if you're already doing all, but there's even more. There's another one that we'll get to much later. You can skip this one, but I normally put it in. It's just easier to remember if you put it in. Dash G, don't worry about what that means right now. And then the name of the program, let's see, hello world, helloworld.cpp, and then dash O, hello_world. That's the name of the program, the output name of the program. You will learn all this in lab, by the way. I'm just showing you this. If we type this, and if I didn't type anything wrong, what will happen is the compiler, named Clang++, that program, that app, if you will run, and it will say, it will do some warning. It will tell us if there are any issues with our code, and then it will take the file, our code, and then produce this file. Okay? Produces this file if I typed everything right, and takes a second sometimes, and there it is. It doesn't tell you anything. One of the things about our computer systems is if you type something to tell the computer what to do, it does it, and then it just says, OK, it doesn't even say I'm done. It just does it. And then you expect that, oh, everything worked out all right. It's one of the interesting things about using Linux and Unix-like terminals, which is what we're going to do you'll see in lab. OK, and then how do you actually get your program to run? You have to type /, which means in the directory we're in, don't worry about the details of that. But then you type hello world. And once you do that, it will actually type out hello world for you, right? So that's going from the actual code. Now, let me show you the code. We are going to use an editor called Vim, V-I-M, in labs. And you should probably use it for your own programming as well. Vim looks like this. It's like I said, there's line numbers down there, and there's all sorts of code in here. All right? And you can go around with your arrow keys. You'll learn all this in lab. You can go around with your arrow keys and whatever. You can't actually type something. Well, I'm typing H right now, and it's going backwards, right? It doesn't make sense. What you do is you type the lowercase I, and that puts you in insert mode, and then you can start typing stuff. OK, you'll learn all this in lab, but this is the editor that we're going to ask you to use. OK, you don't have to. There's other ones, but this is one that we're going to talk about in labs and things. Now, let me show you. This is the program. Let me show you what happens if we make a mistake. Remember the other day I said, what happens if you leave out a semicolon? Does the computer compile it correctly? No. I'll show you this. The computer, let's recompile it like this. And it says, hello world, CP error. And it gives you this big error message, and it says expected semicolon after the expression. See out hello world end L. And then it's hard to see from the back of the room, but there's a little like caret symbol saying, hey, right there you forgot a semicolon. Now, why couldn't the computer just put it there? Well, maybe you didn't mean that. Maybe that's what it thinks the error is, and in fact it's right. And most of the time it's right. But it just tells you, look, go fix your program because I'm not compiling it without that semicolon right there. All right? So we go back up and we say, all right, let's go edit it again. And I put the semicolon back, and then we're good to go. OK? Oops. And then now if we compile it again, it will be fine. And then it will run just fine. OK? So if you get an error message, you won't actually get a program. If you get warning messages, you will, but you'll figure that out when you get to lab. All right, so that's the basic the flow of how we're going to do stuff. Type something up in an editor, compile it, have errors, and then go back and fix it in the actual editor again, and then recompile until it works. All right, so that's how it's worked. That's how it goes. So the program, as I said, is, well, I didn't say it yet. The program is an encoding. Basically, your program is an encoding telling the computer, a code telling the computer what to do in a formal programming language. Ours is C++, right? And coding up the algorithm itself is the shortest part. Like doing the programming eventually will become shorter than doing the problem solving. For now, it's going to take you just as long because you don't actually know how to do this yet. But eventually, you'll get to the point where you'll solve everything out in your brain or on paper or whatever. Then you'll code it up, and the coding will go much, much faster. OK? All right, I want to show you four relatively short programs and describe some of the things about these programs. You will need all this for your homework assignment, like these ideas. OK, we're going to talk about integer math, floating point math, which is decimals. Integers are integers, no decimals allowed. Floating point are numbers that have integers in them, and computers generally break those into two different categories. You can have floating point numbers that have like 0.0, but you can't have integers that have decimal places in them. All right? And then we'll talk about these things called strings, which are the text that you're going to type in. OK? And we'll talk about some basic functions and then some individual character things. All right. In C++, int is what we call a type. It describes the type of the thing we're dealing with. In this case, it describes a type of integer, which is nice because it's basically integer abbreviated, right? Ints can only hold integers. They can't hold numbers that have decimal places in them. Why? Because that's the way it works. In fact, remember, computers can only talk in binary, and you can have decimal binary numbers, but the computer only knows zeros and ones, so there's no decimal in a 0 or 1, right? So you can make decimal numbers, but you have to play some games to do it. All right, so we have a specific type called integers, and you declare integers like this. You say, if I want a place in my computer to hold an integer that I'll decide later, I just say int and then some variable name. The nice thing about variable names is they're up to you. A lot of times we will use short names like x or y or z or I or j or k. But if your integer is going to describe something, like let's say I said to the user, input how old you are. What would a good variable name be for that? Age. Yeah, right? You don't want to say x for the age, because that doesn't tell the person reading your code. By the way, the computer could care less. The computer doesn't care if it's x or age. But the human reading it, and the TA is grading it, by the way, will care if you just use x's and y's and i's and j's and k's. Don't do that. Use things that are definitive. Now, if they're going to be something like coordinates, sure, x and y works great, because that's what coordinates are generally in, right? We'll talk later about when we can use I, j, and k, and there's very specific places to use those. But normally we make our variables a good name that makes sense. Okay? Here is a program. All right, here's another program, and this program is to demonstrate integer arithmetic. What did I say this little / meant? It's a comment. So these first 5 lines, the computer completely ignores when it's compiling your program. That's for the humans. You should always put the following 4 things in your programs. You should put the name of the program itself. That's always a good thing. So somebody opening it up, if it's on your screen, can tell which program you're in. And then you should put a purpose. And the purpose is what the program does, right? You're going to write some pretty long programs, and this like purpose statement can get kind of long eventually, but you just write a purpose. The purpose in this case is to demonstrate integer arithmetic. Not the best purpose in the world, but that's what it is. Who wrote it? Me. What day did I write it? I wrote this way back in September. All right? And then you can start the actual program. I said that every program we're going to use is going to start with these two lines. Hash include less than sign, IO stream greater than sign. All right, that means we're going to use input output. It's tough not to for a program. You don't have to, but it's tough not to make it do anything interesting. Then we're going to use this, which says, hey, some of this things we're going to use, we want the standard part of it so it makes it easier. Do not worry about those details. When you get to Comp 15, you can start to think about those, or later when you're programming. Don't worry about that. All right, the first thing the program goes to when it actually runs is the main. Right? That's where a program starts doing something. And what do you think this line says? Int w comma h. What are we actually doing with that? What are we doing? There you go, declaring a variable w and h, which you correctly interpreted to be width and height, right? Which is very good because down here it's that. That's not a bad one. If I was to rewrite this program, I might actually type width and height for the two variables, just because it's a little bit easier. But for this case, we know we're finding an area, so you can do that. I have two other variables I have declared called area and perimeter. I bet you can guess what those are going to end up holding, right? And then I say cout. Now we saw this in our hello world and some other programs. Cout says the little double less than says everything after this put to the screen, right? The cout output says please type a width and a height. And then I have it's in quotes, and it's got a semicolon at the end. And that's going to print that on the screen. I'm going to show you this in a minute. It's going to print that on the screen. And then once it says that, we need to actually input our numbers. Well, how do we do that? We say cin. Aha. That's a way of saying get the input. And it says cin, whatever we get from input, it goes into w. That's what the other greater than sign say. Put whatever we get from our input into that variable. After that statement, if we type a number, w has the value of whatever we typed. Okay? So that's kind of nice. It's asking for input, and we're going to be able to type it out. And then same thing for the h. And then, hey, guess what? C++ can do arithmetic. The area, what did I say we were going to say instead of equals? Gets. We're going to say the area gets w and then asterisk. And an asterisk looks like this, and it's the shift 8 on your keyboard, and that means times. A lot of people try to do x, and that doesn't work, but x is like, because it's a letter, it's going to be times. Yes?
When you had your integer declaration,
I could have written them all on one line. I could have said int w, comma h, comma area, comma perimeter. It looks a little nicer this way, I think, normally to do it this way. We also have a limit on how many characters you can go across. It's not a limit the computer cares about. It's the limit we care about. You're not allowed to go more than 80 characters over without going to the new line, or we'll take points off on your assignment. Why? Because we don't want to try to scroll left and right on the screen, and 80 characters fits exactly in the thing that we graded on. So yeah, you could do that, but you want to make it look a little nicer. Remember, programs like this are for humans to read, also for computers to compile, but mainly for humans to read in that sense. Yeah, question?
Do you have to declare variables at the very beginning or just before you use them?
Good question. You have to declare the variables up here. Normally, we declare variables at the beginning if we're going to use them later in the program, just because it's easier to see them right there at the beginning and see what we're going to be dealing with. But you don't have to. No, it's generally good practice to do that, though.
Functionally, it doesn't matter.
Functionally, it does not matter. As long you have to declare it before you use it. That was it. Yeah.
So we declare a variable as an integer.
Yeah.
What if that variable is not an integer?
What happens if it's not? The computer actually turns whatever you type into an integer. Yeah. Or it like stops reading after you've typed the integer part. It goes, oh, a period? I don't know about that. I'm going to stop the integer part. I'll show you that, and I'll show you why it can break your computer. Yeah?
How do we start with that?
Because main is where programs start. The people who designed C and C++ said, we're going to start all our programs in the main function, which is what they called it. That's all. Every program has to have a main function. Yeah?
Why there is an N1 after some line that appears?
Over here?
Yeah.
I'll get to that in a minute. So we figure out the area by saying area gets W times H, semicolon. Then we figure out the perimeter. Perimeter gets 2 times W plus 2 times H. Now, one thing about the math that it knows, it does know rudimentary order of operations. So it will do the timeses first and then the addition, right? There are certain times where parentheses are a good idea. It does understand parentheses. So you can do that too. Then it just says, look, I'm going to print out the area. The area is, and then here's how it goes. I say, remember, the double less than sign says everything pointing towards this after this is going to go to the output. The area is, end quote. And then I do another double less than sign, and then I do the area, which is the variable, and it says, oh, go tell me what the area is. And it takes whatever that is equal to and prints it out to the screen. And then we have the end line just to make it print it and then go to the next line. Did that answer your question about the end L? That means go to the next line so it's not all on one long line when it prints out. Okay? And then we do the same thing for the area this way. We can do it this way. We can say the area is also, and then we can do the little arithmetic right in line. And this is a little hard to see up there. We can do the arithmetic right in line like this. We can say the area is also W times H like that. Normally we want to store it in a variable, but sometimes you don't want to. Right? So you can do that. And the perimeter is, and then same thing. We stop the quotes, put the perimeter, put the end line. And then what did we say return 0 does? It says we're done. We're successful with our program and we're done. And that's what it does. It leaves the program. Okay? It actually leaves the function. We'll get to that later. But let me show you this in actual form. This one is integer math. So, all right, let's see. Do I have integer math here? I do. So, Clang dash wall dash wextra dash g integer math.cpp dash o integer math. That will actually compile it. I typed that really fast. I used some special characters to type it too, which made it do it. OK, and then it did all that and it let me run it. So to run it, I type dot slash, and I type integer math, and it says, please type a width and a height. Here's how you can do it. A couple different ways you can do it. You can type 4 space 5, or you could type 4 enter 5, but it will accept either one. Okay? It just stops reading when it needs to. And then it says the area is 20, which it is, and the area is also 20, because remember we did it 2 different ways, and the perimeter is 18. 4 times 2 plus 5 times 2 is 18. Okay? So that's how you go from like the program itself. Now, we probably should have spent a minute or two talking about how to do that, but I just wanted to show you how you use integers to do some calculations. Okay? Question?
So you said you can enter to it by doing either space between the numbers or pressing enter. We don't have to program to define what or where the number is, or
nope. You just say it. The cin command is pretty smart. It'll just, if you're typing 2 numbers, it'll use the space as the delimiter to say when you've stopped typing a number. Now, question came up earlier. What happens if you type like a 4.5 or 4.8 and then some other number? Well, it actually says the area is 0 because it has no idea. What it did was it basically didn't get a number properly into the actual variables because you didn't type an integer and it was looking for an integer. So if you don't type what it's expecting, things can go really weird about it, right? So you got to be very careful about what you're telling the user to expect. Please type a width and a height. Please type integer width. An integer width and an integer height might be a better thing to say. Okay? All right. So, oops, there we go. All right. Other questions on that program? All right. Let's look at some other things. Now, as I said, floating point numbers mean that they have decimal places in them. Okay? We have two different types of floating point numbers. One is called a double. And a double just means it's twice as, quote, big as a regular floating point number called float. All right? We will normally use doubles in class. Why do we use doubles? Because they hold a bigger range of number, and That's really the only reason. You can use floats for most things, but doubles will give you better what we call precision, which means they are more precise when you do the output. Okay? But you do it the same exact way. You say double A means I've declared a variable that can hold numbers with decimal places called A. Float F, I've declared a number that's a floating point number that can hold decimal places called F. All right? Yeah? No, they both can hold integers, generally. They both can hold integers, but the difference is that doubles hold a wider range of numbers. So computers can't hold infinite amount of numbers, right? You have to make cutoffs somewhere. The double has a bigger cutoff than the float. That's about it. All right. OK, so here's our double program. Guess what? It's basically the exact same program, except we've changed things. We've now made our width and our height into doubles instead of ints. And now we can do, it is exactly the same program, except now, if we compile it, let me do this quicker than you might want me to, but let's see, what's it called here? Doublemath.cpp, double math. And when we do that, and then we actually type /doublemath, we can now type 4.7 and 8.3, and we can actually get, I hope, correct numbers here. 4.7 times 8.3, that's about 39. So, well, 39.01. All right. We will talk later about when to use and when not to use numbers, or floating point values. But in many cases, if you can use an integer, use an integer. It's going to be faster. Not that it really matters that much for this class, but it's going to be faster, and it's going to be more precise in the end. You can actually get less precision with decimal numbers because of various reasons that we're not going to go into right now. All right? So anyway, same exact program, but this one uses doubles. OK, there's another one we have to talk about. Remember I said that there was the Yoda program, talk backwards program? Ask for 4 words and then print them out in reverse order that you got them in. You're going to need these things called strings. A string is simply it's a set of characters in a row, that can be either alphabetic characters or digits. It can be digits, or it can be other special characters like a parentheses or something like that. That's what a string is: alphabetic and numeric and other characters. And the Go Jumbos was an example of a string, right? It has alphabetic numbers in it. It's got spaces, which is punctuation, and it's got an exclamation point in there. That's a string. OK? Pretty straightforward. You can also use cin and cout to perform input and output on strings. OK? Strings have cool properties to them, like a size. A size says how many characters a string is. So you can do, it's either length or size. You can use either. But you can also look at individual characters which are of type char. Another type of character is a char. A char is a single character. One character is a char. You can't have AB being a character. That is a string. A is a character, or C or D is a character. All right, there's a lot going on here, but basically we're saying declare a string called first name. I bet you can guess what it's going to hold. Declare an int called name length. Could the name length, in other words, the number of characters in your name, be a decimal number? No, it's impossible, right? I mean, you got a number of letters in there, and that number of numbers is an integer. So in that case, you want the integer, you want the name length to be an integer. We could also say char first letter and last letter, which is the first letter and the last letter of your string, let's say, or whatever we want. It's just characters. OK, so this is going to say, what is your first name? And you're going to type your first name. Then it's going to say your name, and it's going to print out your first name. That's nice. Then it's going to do some stuff on it. It's going to say name length equals first name size. That's how many characters are in your name, the length of your name. If I put in Chris, it would be CHRIS, would be 5 letters, and it would say name length gets the size of the name, which would be 5. So the integer name length would hold 5 if I typed in Chris. Okay? The first letter, here's how it works. We're not going to worry about this notation for a while. I'm showing it you right now just to show it to you, but don't worry about this. The first letter is, which character do you think we start on? The 0th. The first character is the 0th in terms of the actual letter. So the first letter is first name. These are actually brackets. 0 is the first letter. So if I typed CHRIS, the first letter would end up being C. Last letter would be the first name, name length minus 1. If you had what's the name length of this? 1, 2, 3, 4, 5, right? Name length equals 5. Don't worry why I put the double equals there, but it's going to be 5. OK, this is the 0th, the first, the second, the third, the fourth. Aren't there 5 things there? This one's the first one. H is C is the 0th. H is the first, R, and so on. The last one is the name length minus 1. Because there's 5 things here, but we start from 0. OK? So does that make sense that the fourth thing in here, according to our computer science, is going to be the S? And it's the length minus 1. Why do we do that? Well, that's the way we count. So that's that. Questions on this one? If you have questions on that, then you can let me know. Let's see. This one, I don't know why I have this one twice, but I do. So that's the one that we do that. All right. Let's take a few minutes. I don't know if anybody noticed. Of course you did. Why wouldn't you? There's a thing of Wonder Bread, and there's a thing of jelly, and there's a thing of peanut butter. And I have a knife and I have a plate. And what we're going to do is we're going to practice writing out instructions. You may have done this like in 2nd grade or whatever, but we're going to practice doing a problem and a procedure. Here's the problem. I want to create a peanut butter and jelly sandwich. And for those of you from like foreign countries and you're like, why are you guys so obsessed with peanut butter and jelly? We love it. All right? That's why, because it's delicious. All right. So here's the problem is make a peanut butter sandwich. OK? That's the problem. OK? Or build a peanut butter and jelly sandwich. The procedure that we need to do is I'm going to be the computer, and I want you to tell me how to build a peanut butter and jelly sandwich. OK? You can be as explicit or not. I'm going to give you 4 minutes to think about it and talk to your neighbor and write down some steps. If you can't get all the steps, that's fine too. You're going to approximate how many total steps it would have taken you if you can. Let's see if anybody can tell me how to make a peanut butter sandwich in some number of steps. OK? So 4 minutes. Talk to your neighbor. Wait, question? Up to you. How precise is up to you. OK? All right. Go. Write it down. Make sure you write it down. I know you guys love sitting on the seats, which is or sitting down here, but there are plenty of seats. Just so you know, you don't have to sit down here. All right. Thanks. Yep. How's it coming? How many steps? How many? 5? Okay. Okay, not bad. Huh? How many steps? 13. Okay. Okay. What about you? How many steps? 6. Okay. Okay. How many steps?
We're at 9.
9. 9 and counting. Okay. A few more minutes. There are plenty of seats, by the way. I know it doesn't look like it, but there are seats you can. If you like sitting here, that's fine, but there are seats. All right. How many steps? 20. Okay. All right. All right. Hey, Zach. How you doing? How many steps? 4. All right. All right. Not bad. Yeah.
It may be a bit stupid question mark. Where do we write these programs? For example, the code that you showed us. Where would we?
You'll learn that in lab.
Okay.
You do it in an editor on the computers in the lab or from your computer through the lab, through the homework server. Yeah, yeah, that's where you do it there. You can do it on your computer, but it's easier to do it there or through the computer there.
So there we would open like
a text editor. You open a terminal and then a text editor. When's your lab?
Thursday.
Okay, you'll learn it all there. If you want to learn it before then, we can talk. But you'll learn it all there. You don't need to worry about it. Focus on the problems before.
So there's no such thing like MATLAB.
There isn't any. No, it's a little different than that. Yeah. I mean, there is, but we're not going to use those. Yeah.
Are you treating the first name as an array?
You can treat it as an array. Yeah. As it turns out, you are. Yeah. Yeah. You do. Yeah.
Sis, I'm signed up for 10:30 tomorrow. But I didn't realize you had to sign up for the
You don't have to. You should be on the other one. If you're not, is there available on 10:30? You can still go if you're signed up on. Did you sign up on Sis late?
No, I was on Sis.
Oh, really?
Yeah.
Oh. Okay. If that's the one that works for you, go tomorrow. You should be on. All right. 1 more minute. Yeah.
So I was confused about the last letter, the name length. So say you
So how big was mine? How many letters was my name?
first 4.
What's that?
4.
It was 5.
Oh,
There were 5 total letters. We still say how many is still 5. 0, 1, 2. But the first one is 0. But there's still 5 total. It wouldn't have said 4. It would have said 5. So then 5 minus 1 is 4. And then here's the CHRIS, 0, 1, 2, 3, 4, which is 5 minus 1. Right? We can talk more about it in a bit. All right. Time's up. Time's up. Okay. So I went around and I did a little poll, and I tried to figure out who, what the kind of the range was. Who thinks that if they were going to tell you to make peanut butter sandwich, it would take over 15 steps? Raise your hand. Okay. Keep your hand up if it's over 20. Okay. How about over 30? Think you could do it in 30? Over 30? Over 40? How many total? Around.
A full sandwich?
Yeah.
That's like 50.
50, yeah, a full sandwich might take. Okay, so some people thought it might take. So this is the question about how precise. Who thinks they could tell me how to make peanut butter sandwich in less than 10? Raise your hands. I know I saw a few. Okay, less than 10, less than 10. Okay, how about less than 5, or 5 or less? What are you raising? Okay, I'm going to give you a chance. 5. You got 5 steps to teach me how to make a peanut butter sandwich. What's your name? Ben. Okay, Ben is going to tell us how to make peanut butter sandwich in 5 steps. Go. This is me. I'm the computer. You got to tell me how to do it.
Step 1
1.
is, I just want to make sure this,
You can read them out.
the number sign include.
Okay. How about how about translate it to English?
Okay.
Yeah.
We're going to use the standard peanut butter construction library.
The peanut butter construction library. There is no peanut butter construction library. You're the peanut butter construction library. You're creating it. Okay, good. I have a feeling I know where you're going with this, but okay, so too much information, not enough, not smart enough. Me, I'm not smart enough for that one. Yeah, you had a question or a comment? You got 5 steps?
Yeah, I got
Go.
Step number 1.
Yeah.
Lay out 2 pieces of bread.
Okay. I mean,
Step one, open all things on the table.
okay. Open all things on the table. Okay. Okay. Do I need to open anything else? Fork or anything? Or a knife? Okay. Next step. That's really 3 steps, but okay. Keep going. I know, but it took me 3 things to do it. Okay, everything's open.
Step number 2.
Step number 2.
Lay out 2 pieces of bread.
Okay.
I realize that I did not think this through.
Okay. Starting here. Who thinks starting here they can give me 5 more steps to do it? Okay, 10. Okay, that's a lot of steps. Okay, go.
Open bag of bread.
Done.
Take out 1 slice.
Take out 1 slice. Okay. Somebody doesn't like the end. All right. This one all right? It's not whole wheat. I'm sorry. Yeah.
Open peanut butter.
Done.
Put peanut butter on slice.
Okay. There. Okay, hold on. All right. Remember, I'm not a very smart man. All right. Keep going. Okay.
You're gonna then put that peanut buttered slice on the plate.
Okay, I actually did that. All right. You're right. I would have had it in my hand. Okay, good.
Maybe another step.
Yep, there you go.
Then you're gonna take out another slice.
I can do that. Yep. This one okay? All right.
You're gonna open the jelly.
Done. Okay.
You're gonna put the jelly on the slice.
All right, I'll do it this way.
And you're going to combine slices.
Okay. Done.
Put the finished product on your plate.
Okay. Don't try to tell me to eat this because I'm not eating this. All right. So somebody who thought there was going to be 100 steps. Start off your steps.
Thin bag with hand.
Got it.
Grab plastic bag with other hand. This is assuming the bag was closed to start.
Oh yeah. Assuming the bag was closed. Yep. Okay.
Pull back until bag ruptures.
Oh, okay. So rip it open. Okay. All right. That would work. I will give you that it works. Sometimes you can write programs in computer science that will work but aren't particularly a good idea. But yes.
Release torn bags.
Okay.
Seize 2 slices of bread.
Like I'd have to go inside, but okay.
Well, this is assuming you already had a big hole.
Okay. Oh, that's right. There's the hole in it. Okay. 2 slices of bread. Okay.
Move hands to plate.
Move hands to plate.
Release bread on plate.
Release bread on plate. Okay. So this is very good. This is very good. I don't think we need to go through all 100, but you see how that would probably get us a little bit closer. I still might be too stupid to actually get the paper, to use the knife properly or whatever. And I bet I could probably fool you if you didn't know what I knew. But the point of this whole exercise was not to make me look like a fool. Well, maybe a little bit, but part of this was to show you that, look, computers really are dumb, and your procedure needs to be exactly the way the computer understands it. If you say, take 2 pieces of bread, and the bread thing is still closed, you're done, right? The computer might try to do something. The compiler might say, I don't know how to do that. I don't know, need enough information. Now, we had somebody who said, look, use the peanut butter library that does this, right? Great. Those are things that we may not have. There is no average 5 numbers library or average 3 numbers library. There is no library that says write a sentence backwards, right? You get to write those programs yourself, but you have to be extremely explicit. By the way, I never actually got to any peanut butter or jelly in this, but too bad. But you see the whole idea is you have to be really precise and you have to understand the rules. And sure, I cheated a little by not really telling you the rules, but you have to know how to do it explicitly. And trust me, the computer is just that dumb. All right, it knows some things, and we're going to teach you some things. Notice that we told it exactly. We said, look, we're creating two variables called W and H. You couldn't have used them otherwise. Other languages you could, by the way, but it will create them kind of as you go along, right? It said, what do I want to read in? I want to read in W. How do I do that? From C in, and it's explicitly telling you how to do that, right? And sure, it's not quite the same. You don't, now, I should say that the underlying machine code to say C in W is probably hundreds of lines long, by the way, because the stupid computer needs to know to go to the keyboard and read in from the keyboard. It needs to know that. It needs to stop all the other processes or kind of wait until the keyboard gets typed. And it needs to know where in memory to temporarily store this. It can't just store it explicitly in W immediately. It has to know where to temporarily store it. It has to know that what if the clock on the computer flips to a new day? It needs to update all the calendar stuff. Well, that has to happen in the background. So all of these things are like way low-level stuff that you don't need to know, but you need to know enough medium level, and we call this high level, but it's not really that high level stuff to tell the computer exactly what you want it to do. Okay, so that's there. And if someone comes up with an actual peanut butter and jelly sandwich making thing, send it to me on email or put it on Piazza. Say, this is how I would have done it. You do that. All right, so that's how we made a procedure, right? We said it took from between 5 steps where I ended up with something I would have had to eat plastic to hundreds of steps where eventually I might have gotten it, although it did break the bag in that case. Okay? What went wrong? Billion things that could have gone wrong, right? To do the actual thing, we need to know billions of things, right? By the way, you could have given me thousands of steps, and if I didn't know how to grasp the knife, or even say knife, grasp the knife with my hand, right? I wouldn't have, if I didn't understand English, if I didn't understand what knife meant, if I didn't understand which one was peanut butter, right? I mean, if you were from a country that had never seen peanut butter and jelly, and I said, which one's peanut butter, right? You'd have no idea. Right? Anybody from Australia in here? No, they don't really have grape jelly in Australia. When I lived in Australia for 2 years when I was in the Navy, and I had to get my friend to send me grape jelly because I wanted it. Right? They have like black currant jelly, which is not the same. Trust me. All right? Okay. So as I said, your program for homework is going to involve a little bit more than we've even learned right now. I'm going to quickly show you some things that we will go over again on Thursday. And then at that point, you'll have enough information to do it. So after today, you'll have enough information to think about doing the homework, but you won't, you really should solve it on paper and so forth first. Think about the problem in broad strokes first. All right, we talked about ints, floats, doubles, strings, chars. There's another type of data structure or data type called a bool, which is Boolean. It stands for Boolean, and it can either be true or false. Okay? Boolean values can be true or false, and we use them all the time in C++. Okay? 3 is greater than 5. Is that true or false? It's false. So the expression 3 is greater than 5 has a value of false. Okay? Computers have the ability to do exactly this. You can say 3 is greater than 5, and it will know that that statement is false because it knows how to compare numbers. Okay? Here is an example. Int main blah, 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 same thing as we've seen before. I didn't put my name and all that. You should always put that in yours. Bool b1 and b2. Create two variables that are Boolean values. Okay? b1 gets 3 is greater than 5. Well, we just said that 3 is greater than 5 is a Boolean value, which is false. So what's the value of b1 going to be after we say b1 gets 3 is greater than 5? It's not going to be 0. Now, in the lower level, it may be, but do not call it 0. In C++, we're going to say it's either true or false. And C++ understands true or false. Okay? The whole 1 or 0 thing, you can think about it that way if you really want to, but don't. No, don't for this class. It is either true or false, and in this case, b1 is going to be false. Okay? It's not an integer as far as C++ is concerned. b2 gets 5 is greater than 3. b2 is now going to be true. Okay. And if we see out b1, now this is what happens when you try to see out this. It actually says 0 and 1. Well, that's because cout isn't smart enough to handle Booleans correctly. Okay? It isn't quite smart enough to handle that correctly. All right? We'll get to how we can actually print those out later. Okay? But in our case, underneath the covers, well, as far as we're concerned, it's going to be true or false. In this case, B1 is going to be false. B2 is going to be true. Okay? If I ever put what on the board, it means what's going on. Yeah?
Could you also type in true or false into B1 and B2 when it's in the parentheses, or would that not work?
You could. You could say B1 gets lowercase f-a-l-s-e. And that would work fine too. It's a way, and you didn't even need the parentheses as it turns out. Right? Yeah?
If B1 and B2 were ints,
Mm-hmm.
and we did B1 equals 3 greater than 5, or gets 3 greater than 5, etc., would they do anything? Would they say 0 and 1?
Yeah, so C++ does do some conversions. The question is, if B1 and B2 were ints, would it convert it to the 0 and 1? It would, but don't do that. We would actually take points off if you tried to make all your Booleans be integers, because we want them to be what they really are. And if you're comparing two numbers, they can either be true or false as far as we're concerned. Okay, so just think of it that way. Okay. All right, there are lots of different symbols we can use. All right, less than, greater than. This is how you do less than or equal to. There is no like less than and then with the equals next to it, right? This character, although it exists on the not on the keyboard, exists. That's not what we mean. We have to type it with two characters, less than and then an equals. It's not the other way around, by the way. It is less than and then an equals. So not this, because you won't even find that on your keyboard, but you will find a less than and you will find an equal. That means less than or equal to. Okay? Greater than or equal to is equal to. Remember how I said that I hate the fact that C++ says A gets B and it's in a single equal sign? If you want to say a Boolean value 3 equals 5. Is that a true statement or false if this means is equal to? It's false, right? 5 equals 5 would be true because 5 is equal to 5. And the equals means is equal to. I wish they'd done it differently, but it's too late now. All right? And there's also one called not equal, right? Not equal is the exclamation point, which kind of looks like it might be a slash, right? Exclamation point equals means is not equal to. So 3 is not equal to 4 is also true. Okay? So that's how those work. All right? The double equals sign is the one that people kind of always forget when they start out. If you said 3 equals 5 like this, 3 gets 5, right? It wouldn't actually this would probably not even work, right? But if you said if 3 equals 5, still wouldn't work. If you had a variable in there and said that, it would try to set the variable. You don't want to do that. So be very careful when you use equals versus the equals sign. There are a couple other ones as well which are you use on Boolean values. And, well, true if both are true. True and false. Are they both true? So true and false means false. Or is, by the way, you use two ampersands, the shift 7, I believe it is, shift 7 on your keyboard, ampersand. You use two pipes. Those aren't exclamation points. They're like, on my keyboard, they're shift backslash, which is above the return key. That's what that is. That's what order. I would just use these ones. You should probably know these, but these are the ones you can use as well. You can use either symbol. Or means if true is one or the other is true. You've done some basic logic before, I'm sure. True or false, well, one of them is true, so that means true. Not means the opposite of whatever it is. So not true is false. Not false is true. That's all those mean. Okay? All right, two vertical lines, shift backslash is what those are. All right, last thing, and then we're going to go back over this on Thursday. You're going to need this for homework 1, which is why I'm just showing it to you briefly. You'll learn a little bit about it. Well, you won't learn about it in this week's lab, unfortunately. But I'm going to show you enough programs on this on Thursday that you'll be able to understand this stuff. Here's what this is. You can have a statement that says, if some Boolean expression do something. You can also say else. In other words, if it's not true, do something else. So if something is true, do something. Else, do something else. Do some other thing. Okay, here's how you do it. Pick a positive integer. read in the number from input. If the number is less than 1, print out that's not positive. Else, print out thank you. Okay? That's a pretty simple program, but that's how the if-else statement works. It's actually one statement. You can do it like this. I will have many more examples about this later. Okay? For an input, one sec. For an input of 4, it would say thank you. Why? Because the number is not less than 1. Right? If the input was -1, it would say that's not positive. Okay? I will see you guys Thursday or in lab.